Okay, guys, so chapter 11 in your textbook talks about three different phenomena, basically generalization, discrimination, and stimulus control. So, what does that mean? Well, typically, when people think about operant conditioning, right? So we've talked about operant conditioning enough that we know the contingency fairly well, right? So an organism, whether we're talking about a human or a primate or a rat or a pigeon, learns to associate a particular behavioral response with an outcome, whether it's a rewarding outcome or a punishing outcome, right? So, because we think of operant conditioning in these very discrete terms of a response and a consequence, people usually think of operant learning as a response to a very specific stimulus. However, operant conditioning wouldn't be very useful, right, if a particular response had to be identical in every situation, right? So those kind of constraints would seriously limit the value of operant learning. So, for example, um, we've all kind of encountered this kind of ubiquitous stimulus in our lives of the traffic light, right? So traffic lights obviously are universal in the sense that a red light means stop, a yellow light means slow down, and a green light means go, right? But there's also some variability in traffic lights. Obviously, one of the factors that varies is the location of the traffic lights. Also, the general apparatus that makes up the traffic light can be different. So sometimes they're really fancy, right? And they have this like, I'm trying to describe it, but like a very elaborate mechanism where it's enclosed in this big box, and sometimes you have voice activation with the traffic lights that say either stop or go, whereas other traffic lights are kind of flimsy looking and they hang from wires and they look kind of precarious, like they're going to fall over at any particular moment, right? So every traffic light would have to resemble every other traffic light in size, shape, color, and location, or people wouldn't know what to do when they approached a traffic light, assuming that these contingencies between a particular stimulus and a response, or a particular response and an outcome, were that rigid. But fortunately, we can carry over what we learned in one traffic light to when we encounter another traffic light, right? So this refers to stimulus generalization, right? And fortunately, we can also discriminate between similar stimuli, right? So for example, we can just discriminate between a green light, a red light, and a yellow light. Okay? So that's essentially what we're going to talk about in the context of this lecture. So we've all kind of encountered this situation as young children, right? Where we encounter a puppy for the first time, or maybe a cat, right? So you point very excitedly and you ask your parents, what is that? And they tell you, oh, honey, that's a kitty or that's a puppy, right? And so, given the name for that particular stimulus, you start to think about attributes. Okay, so if we're using this picture, dogs are gold colored. They have long kind of manes of hair. They have big feet and they have a tail, things like that, right? Or cats have gray and white fur, a long tail that stands up, and little white kind of socked feet, right? Um, and then, okay, maybe you encounter another dog that's not a golden retriever, but a golden lab, right? Or maybe you encounter a cat that is gray and white but doesn't have the socked feet, the white feet. But you're able to generalize or carry over your general knowledge of your previous cat or dog experience to that slightly new exemplar in the form of another cat or another dog, right? So that's stimulus generalization. And then, of course, we have stimulus discrimination, right? So even though you've only encountered um, one single dog or one single cat, if you encounter another another animal, okay, like a raccoon, right? An animal also has gray and black fur, okay, and maybe they have specks of white as well, but you're able to successfully discriminate between a cat and a raccoon based on other perceptual features, right? So that's generally what we're talking about is when we recognize the same animal, even when it's a different size, has different colored fur, it's a different length, or maybe it has a different textured fur, that's stimulus generalization. So putting something into the same category, even though there might be subtle differences, versus stimulus discrimination when we do not recognize the same animal because of different characteristics, right? So we don't confuse a gray and white kitten with a gray and black raccoon. So, when we talk about generalization, we're generally referring to the tendency for the effects of learning to transfer or carry over to some new context, right? So, for example, we learn about percentages and how to find them in elementary school, and we learn it as this very kind of semantic, detached thing. But as an adult, we can reference that earlier learning experience in a new context when we calculate a tip for a server, for example. So there are actually multiple types of generalization that learning psychologists have studied over the years. So we're going to talk about 4 different types of generalization. So the first is sometimes referred to as vicarious generalization, and that's in reference to generalization across people. So a basic definition is that this occurs when a behavior learned in one context or with one person is exhibited with different individuals who were not part of the original learning scenario. So, for example, a child learns to say thank you when prompted by their parents. Later, the child spontaneously says thank you, for example, when receiving a gift from a teacher or a friend, even though those individuals were not present during the initial learning of the thanking behavior. And there's a lot of research on this. So, for example, in Bandura, Ross, and Ross's classic 1961 study, children who observed an adult model behaving aggressively toward a Bobo doll, later these children imitated the aggressive behavior not only toward the Bobo doll, but also in other settings and toward other toys and objects, and sometimes across, fictional characters, right? So individuals or individual toys in this context that weren't present during the initial learning were still subject to aggression. Another example of generalization is generalization across time, which is also referred to as response maintenance. So this refers to the continuation of a learned behavior over time, even after the original training or the reinforcement that came with the training has now ceased. So one way to think about it is it's kind of the opposite of forgetting a contingency, right? It's maintaining a learned contingency over time, right? So an example is a student who learns to solve math problems during the semester, right? Months later, without additional practice or without the reinforcement of wanting to get a good grade on an exam, the student can still solve similar problems correctly, indicating maintenance of that skill over time. So one example of a supporting study was by Bayer and colleagues, and they conducted a study where they taught children with developmental disabilities to imitate certain behaviors. So, for example, to wave hello and goodbye, and then they looked at whether or not they spontaneously demonstrate these behaviors after a period of time has elapsed. So, and indeed, what they found is that the children continue to demonstrate these behaviors weeks and even months after the initial teaching session ended. So, for example, a child who was taught to wave when prompted with wave goodbye, several months later during an unstructured interaction, the child spontaneously waved goodbye. So number 3, generalization across behavior, also known as response generalization. So this type of learning occurs when learning one behavior leads to changes in similar or related behaviors that were not specifically taught, right? So one very straightforward example is if a person learns how to throw a ball with their right hand without direct training, they discover they can also throw a ball with their left hand, although it may not be as proficient initially as with their dominant hand that they learned first. So other studies by Stokes and Bayer in the late 1970s actually reviewed a multitude of studies and found that often interventions targeting specific behaviors often led to improvements in other non-targeted behaviors. So, for example, these researchers worked with children with developmental disabilities. Um, and for example, they taught them how to spell words. So, one study trained children to spell words by writing them with a pencil. Surprisingly, these children also improved in typing the same words on a keyboard, even though that wasn't directly taught to them, right? So the initial behavior of handwriting words generalized to correctly spelling the same word when it's typed. And lastly, perhaps the most important and most thoroughly researched type of generalization is generalization across situations or contexts, also known as stimulus generalization. Right? So this happens when a behavior learned in one context or situation is exhibited in a different context or situation. So for example, a dog is trained to sit when hearing the word sit in a quiet room. Later, the dog obeys the command to sit when in a park, even though the environment is different and more distracting, right? Um, Another example, a study by Gutman and Kalish in 1956, they trained pigeons to peck a key when a light was illuminated at a specific wavelength, and they found that pigeons also pecked keys illuminated by wavelengths similar but not exact to the training wavelength. Right. So these are all examples of different types of generalization that humans and other organisms can learn fairly easily. So kind of going back to the most well-known example of stimulus generalization, right? So stimulus generalization is the tendency for changes in behavior in one situation to spread to other situations, right? Another way to define it is the tendency to respond to stimuli that were not present during training in the same way that you respond to stimuli that were present during the training, right? Um, so, for example, going back to when you train your dog to sit, you hope that will generalize beyond your distraction-free home environment to more distracting environments outside, right? Um, Other examples, right? One example from Pavlov, okay? So in Pavlovian conditioning, a dog may learn to salivate to the sound of a tuning fork that's vibrating at about 1,000 cycles per second, right? After this initial training with the tuning fork that's vibrating at about 1,000 cycles per second, the dog may generalize this salivation response to another context where there's still a tone or a sound that's vibrating, but maybe instead of vibrating at 1,000 cycles per second, it's vibrating at 1,100 cycles per second or 900 cycles per second, right? So in that context, the dog has generalized the salivation response to the tone, not only to the exact frequency of the tone during training, but to other similar frequencies. Okay. Another example from Pavlovian conditioning that's more fiction than fact, as it turns out, is Watson and Rainier claimed that after learning to fear a white rat, after the uh, conditional stimulus of the rat came to elicit an unconditional stimulus of a loud noise, right? They claimed that rats fear, or that little Albert's fear of the rat generalized to other white furry things. So the fear of the rat generalized to another context of seeing a white rabbit or seeing a bunch of white cotton balls or seeing a Santa's beard mask that was white, right? And so if it were true, that would be another example of stimulus generalization. But as we've talked about, there's limited evidence to support that. But nonetheless, um, and then in a final study looking at fear conditioning in college students, one researcher by the name of Hovland began by pairing a tone with a particular pitch, which is the conditional stimulus in this case, with a mild electric shock, which was the unconditional stimulus. And then he measured the galvanic skin response, which was a measure of emotional arousal or fear. And after 16 pairings of the conditional and unconditional stimulus, Hovland then presented 4 tones, one of which was the exact tone that was presented during learning. The results showed that the galvanic skin response indicating fear spread or transferred from the original tone to the others. The less a stimulus resembled the conditional tone or the conditional stimulus of the tone, the weaker the conditioned response of fear. And so the researchers found what's called a generalization gradient, whereby the more similar the other 4 tones were to the initial conditional stimulus or the initial tone, the higher the galvanic skin response, indicating more fear, and the less similar the new tone was to the initial tone, the lower the physiological arousal or the fear response was. right? So college students showed fear from a tone paired with shock to other similar tones, but less generalization to more dissimilar tones. So just like we can talk about generalization in the context of Pavlovian conditioning, we can also talk about it with operant conditioning. So, for example, in 1898, Thorndike observed that a cat who had learned to escape from box A by clawing, when put into another box, showed a greater tendency to claw at things than it instinctively had from the start. So, in other words, the clawing response generalized from boxes A to boxes C and G. In another classic study, pigeons were trained to peck a disc of a particular color and later given the opportunity to peck a disc when it displayed various colors, including the same color that was used during training for 30 seconds each. Pigeons pecked the disc most frequently when it lit up with the color used during training, but they also pecked the disc when it lit up with other colors. As the generalization gradient revealed, the more closely the disc resembled the training disc, the more often the birds pecked at it. If a disc lit up in almost the same color as the training, the birds pecked at it almost as much as they did during initial learning. Whereas if the disc showed a very different color, the pigeons very seldom touched the light. Generalization goes beyond highly specific acts like disc pecking. So, for example, broader behavioral techniques also generalize. Right? So, for example, researchers found that rewarding people for making um, um, more of an effortful response increases the level of effort they make for other tasks, right? So if you um, reinforce a high level of effort for an initial task, okay, that level of effort will generalize to other tasks as well. And that is a way to teach what we call industriousness. Um, so we've also seen, for example, that generalization will proceed following both extinction and reinforcement, right? So rats that were trained to press a lever for food um, after they were on extinction, they were not only less likely to press the lever that they were trained on, but they were also less likely to press levers in new Skinner boxes, right? So the extinguished response of lever pressing generalized to other levers or other contexts as well. Um, and similarly, we see the same generalization gradient for punished behavior as well as reinforced behavior, right? So pigeons that were punished for pecking a disc when it was a particular color reduced pecking overall, not just to that specific color, but also to similar colors. So, over the years, researchers have discovered a multitude of ways to increase stimulus generalization. So, the easiest way might be to elicit the behavior in a wide variety of situations. So, for example, if you want a pigeon to learn to peck a disc, regardless of the color of the disc, then you would reinforce all of the different potential stimuli or the potential colors that the pigeon could encounter, right? Similarly, if you're teaching a dog to sit, right, you would have the dog first sit when you're alone with the dog inside your house, like in your kitchen, and then maybe in your living room, and then with one other person present, and then two people, and then from indoor settings to outdoor settings, etc. You can also provide lots of different examples of situations in which you would provide reinforcement, and also vary the nature of the reinforcing consequences, right? So sometimes you reinforce your dog with food, and then you reinforce your dog with praise, and then maybe first you start with an FI schedule of FI1 or FR1, where you reinforce every single instance of sitting, and then you stretch the ratio out to maybe every third time, right? So if you provide this degree of fluctuation, right, that behavior is going to end up generalizing to a wide variety of situations. But reinforcement is not without the potential for negative consequences. So one very prominent, or excuse me, not reinforcement, generalization. Generalization. So generalization, while allowing the organism to demonstrate a behavior adaptively and across a number of different situations, also can cause problems, right? So what is one example of a problem that arises from generalization? Well, generalization can be a problem, right? If an organism, whether we're talking about a human being or an animal, generalizes from a lack of success in one situation by assuming that they're going to be unsuccessful in other situations, right? So, for example, Carol Dweck is a very famous developmental psychologist who studies cognition and a number of other processes related to education. And so Carol Dweck, in one of her earliest experiments, basically took elementary school children and gave them a very difficult problem, a very difficult word problem for which they could not arrive at a solution. So it was basically a problem that was impossible to solve. And so some of the kids were given the impossible problem, and then they were given a problem they were actually capable of solving. And she knew they were actually capable of solving it because when she looked at a second group of kids that were given just the solvable problem without the unsolvable problem first, they were able to arrive at the solution very easily. So she demonstrated one of the problems with generalization is the tendency to give up. So when she first gave the kids the unsolvable problem, very few of them actually successfully solved the easier problem. And that's because they basically assumed that there was no point and that they shouldn't continue, right? So one problem with generalization is it can facilitate the tendency to give up, or it can lead to things like response suppression, where the animal or the organism isn't actually doing anything. It can also increase problematic behaviors, right? So if a child learns via observation, for example, to act out aggressively toward a Bobo doll, and they generalize that level of aggression not only to other toys but also people, okay, presumably at least theoretically that could influence the incidence of problematic violent behavior, right? We also see how generalization on the part of animals can sometimes lead to people getting injured. So, for example, bears who have a really strong prey drive typically when they encounter another bear or a deer or someone that is competing for their food source, or another animal competing for their food source, they will generalize when they see humans near a food source that they are also direct competition, and so they will respond aggressively to humans, right? So that's an example of a situation where where um, where animals generalize the behavior that they have toward prey to humans, right? With obvious unfortunate consequences. Another case was an Inuit child that was pretending to be a seal. And he did so convincingly that a dog came along and assumed that he was a seal, and ended up viciously attacking him. And the child, unfortunately, died as a result of that. So these instances of generalization on the part of wild animals can sometimes have really devastating consequences. Another example of the unfortunate consequences of generalization is through stereotyping and prejudice and hate crimes that stem from that prejudice, right? So, for example, if you assume that people, members of extremist terrorist groups, right? Um, Such as the Taliban, generalize to all people of Arab descent, right? Then that's an example of faulty generalization that can sometimes lead to hate crimes and so forth. So just like we can talk about stimulus generalization, we can also talk about discrimination. So stimulus discrimination, sometimes just called discrimination, is the tendency for behavior to occur in certain situations, but not others. So scholars usually define it more narrowly as the tendency for behavior to occur in the presence of certain stimuli, but not in their absence. Right? So basically, discrimination and generalization have an inverse relationship. The more discrimination, the less generalization, and vice versa. Generalization gradients, therefore, reflect the degree of discrimination. A relatively flat generalization gradient, okay, indicates little or no discrimination, whereas a steep gradient indicates comparable discrimination. So, one of the things that we talked about earlier is that the more a stimulus resembles the training stimulus, the greater the degree of generalization, right? So you can likely guess that the less the similarity of the stimulus that a new stimulus has to the training stimulus, right? The higher degree of discrimination. So a pigeon, for example, that has learned to peck a yellow disc for food will likely peck discs of a similar color, but perhaps not a black disc. So just like we have procedures for teaching generalization, we also have protocols by which we can teach organisms to discriminate. And that's true for both Pavlovian and operant conditioning procedures. So we can start with Pavlov. So obviously Pavlov used classical conditioning, right, to teach dogs to salivate, to atone, for example, right? So if a dog learns to salivate not just to atone, but also to a bell, we would call that generalization. Just like, and we can apply the same exact principle to discrimination, right? So, for example, if Pavlov were to place food in the organism's mouth after a tone, okay, we would call that the CS plus, or the um, or the conditional stimulus that regularly pairs with the unconditional stimulus, right? In contrast, if every time the bell rung, no food was provided in the organism's mouth, right? Then they would learn very quickly to make the salivation in response to a tone, but not to make the salivation response in response to a bell, right? So in this context, the CS minus is the bell because it's a stimulus that is not paired with the US, right? And Pavlov actually excelled at teaching his animals to discriminate successfully. So, for example, he could teach dogs to salivate to different volumes. So, for example, they would salivate to a different volumes or even beats per minute. So, for example, if a dog learned to salivate in response to a metronome, Pavlov could teach the dog to salivate in response to a ticking metronome that ticked at a rate of 96 beats per minute, and not salivate in response to a metronome that ticked at a rate of 100 beats per minute. Similarly, Pavlov could teach animals, or dogs in particular, when they saw a rotating object that was rotating clockwise. He paired that with the arrival of food, but there was no food presented when the object rotated counterclockwise, right? So basically, animals can learn to distinguish not only between a buzzer and a bell, but also between an object rotating clockwise and an object rotating counterclockwise. And they can also distinguish between different volumes of a particular sound, different pitches of a particular tone, different geometric forms, different temperatures, and so on, right? And like I said, one dog learned to salivate at the sound of a metronome that ticked at a rate of 100 beats per minute, but not when it ticked at a rate of 96 beats per minute. So basically, animals have a remarkable capacity for discrimination training in Pavlovian conditioning, but also in operant conditioning. For example, it's very easy to teach a rat to lever press, and it's very easy to teach them to lever press only under certain circumstances, right? So you can teach a rat that if it presses a lever when a light comes on, okay, the stimulus of the light coming on is referred to as an SD stimulus, right? Because that stimulus is going to receive reinforcement. But if the light doesn't turn on, the rat learns that the lever press will not be reinforced, right? So that's referred to as S triangle or S delta. Okay, so basically the animal learns if the light is on and I press the lever, I get reinforcement. But if the light is not on and I press the lever, I won't get reinforcement. So in effect, they learn to discriminate between two different situations and only follow through with the desired behavior in the appropriate situation when it's going to lead to reinforcement. So basically, we see discrimination not just between stimuli with Pavlovian conditioning, but also with operant conditioning as well. Right? So any procedure for establishing discrimination is referred to as discrimination training, and a discriminative stimulus In the context of operant learning, is any stimulus that signals either that a behavior will be reinforced or that it will not be reinforced. And in Pavlovian discrimination training, discriminative stimulus refers to a CS that is associated either with the appearance of the US or with the absence of the US. So in simultaneous discrimination training, the discriminative stimuli are present at the same time. So in a classic experiment, Carl Lashley put a rat on a small platform before two cards placed side by side, which you see in the figure. The rat could distinguish the cards in some way based on a perceptual characteristic, such as one card having horizontal stripes and the other having vertical stripes. So one of the cards was locked in place. So if the rat jumped at the locked card, it would hit the card and fall to the net below. The other card could also move, so if the rat jumped toward it, the card would give way and the rat would land on the other side. Whichever choice the rat makes, it remains unharmed to the jumping stand and it returns for another trial, right? So basically, if you were a rat, like it shows in the picture, you would be placed on a small platform and you would see two different cards that had obvious characteristics that differed or that were discriminable, right? So you would see on one side a card with vertical stripes and on the other side a card with horizontal stripes. And so if you were a rat, you would jump toward either one of the cards, okay? But for one of the cards, after you made the jump, you would get reinforced with food, right? So if the rat jumped toward the correct card, they would get reinforcement. So the position of the cards varied so that sometimes the reinforced card was on the right side and sometimes the reinforced card was on the left side. So the rat soon learned to jump on either the right or the left, depending on what side the reinforced card was on. So unsurprisingly, after just a few trials, the rat very quickly learns which side to associate with the reinforcer, or which card, rather, to associate with the reinforcer. So in another type of discrimination training called successive discrimination training, animals are presented with a randomly alternating reinforced stimulus and non-reinforced stimulus. So in this particular experiment, the horses were trained to lever press using their lips in the same way that rats learn to lever press. But lever pressing was only reinforced in certain circumstances, right? So if a small circle, 1.5 inches in diameter, was presented, okay, that meant that lever pressing failed to result in a reward of grain for the horses. But if it was presented next to a larger circle, or if a larger circle of 2.5 diameters was presented, then that would signal to the horse that lever pressing was going to get reinforced with grain. And so the horse learned very quickly to discriminate between those two things. Relevant to this picture, you can also train horses to discriminate between letters. So, for example, you can reinforce the letter V and not reinforce the letter X, and the horse will learn which letter, which screen press will lead to reinforcement in that case, pressing on the letter V or pressing on the letter X. In a procedure called matching to sample, animals must select from two or more alternatives called comparison stimuli and choose the stimulus that matches the standard or the sample. So the comparison stimuli include the SD stimulus that matches the sample and one or more S delta stimuli. So for example, a red or green light may illuminate a sample disc on the wall of an experimental chamber. On some trials, the disc will light up red. On other trials, it will light up green. After a short time, the sample disc goes dark and two comparison discs, one red and one green, become illuminated. The reinforced stimulus, or the SD plus, is the disc that's the same color as the sample. So if a pigeon pecks the comparison disc matching the sample, it receives food. If it pecks the other disc, it receives nothing. So to obtain reinforcement, the pigeon must successfully discriminate between the disc that matches the sample and the one that does not match the sample. A more complex match to sample match to sample task does exist though. So for example, a researcher may require a bird to peck a disc that differs from the sample, which is a variation of the match to sample task called oddity matching or mismatching. So increasing the number of variations in the sample and or comparisons between the disc could also make the match to sample procedure more confusing or more difficult. So for example, the sample may alternate among many different colors like red, green, and blue, and the comparison discs may also light up red, green, blue, and yellow, right? So a match to sample is a discrimination training procedure in which the task is to select from two or more comparison stimuli the one that matches the sample stimulus. A matching to sample task involves selecting from two or more alternatives a stimulus that matches the sample. So for example, pigeons see a disc light up red, which is the sample, and then they must choose from either a red disc or a green disc. And if they successfully choose the matching red disc, they get reinforcement. And oddity matching is a variant of match to sample. And what differs is is how complicated of a procedure that is, right? Um, so with oddity matching, they basically have to choose the opposite color, right? So if the sample lights up red, they would have to choose the answer choice that doesn't match, or the green light. So another form of discrimination training is errorless discrimination training. And just like the name suggests, errorless discrimination training is a method designed to teach discriminations while minimizing the potential for errors. So this was first introduced by Herbert Terrace in the 1960s. And this procedure is unique in that the incorrect stimulus is presented in a way that significantly reduces the likelihood of a response, gradually increasing the difficulty as the learner becomes more proficient at making the discrimination, right? So let's say we're trying to teach an organism, for example, a discrepancy or discrimination between a red light and a green light, right? So if a pigeon pecks at a red light, they receive food, but if they peck at a green light, they are not reinforced, right? So, what are some key elements of errorless discrimination training, right? Well, the first element is initial weak presentation of the incorrect stimulus. So the incorrect stimulus, or S delta, is initially presented in a weakened form. So this could mean presenting a green light with reduced brightness, presenting it for a shorter duration or less intensity, which makes it less likely that the pigeon will respond to it, right? So, for example, in training a pigeon to discriminate between a red disc that always results in reinforcement after it's pecked and a green one, the red disc could be presented at full strength for 3 minutes, and a green disc could be presented for only 5 seconds, and it's very dim instead of being lit to the full capacity, as is the case with the red light, right? The second element is gradually increasing the intensity of the incorrect stimulus, or the S delta, right? So over time, both the intensity of the green light in terms of how saturated and bright it is, as well as the duration, are increased from 5 seconds to 5 minutes, like the red light is. And so what that does is it ensures that the subject, in this case the pigeon, develops a tendency to not respond to it, right? And then we, of course, need reinforcement of the correct stimulus. So the correct stimulus is presented at full intensity from the start, and that responses to that stimulus are consistently reinforced, right? Um, so one of the main advantages of errorless discrimination is that because we are minimizing the potential for errors, right? The pigeon or whatever organism we're talking about is going to experience less frustration, less emotional arousal, such as anger or anxiety, causing them to be more calm and focused on learning. So example studies. So the original study conducted by Herbert Terrace, he trained pigeons to distinguish between a red disc and a green disc. The red disc was presented at full brightness and for longer durations, while the green disc was initially unlit and presented for only 5 seconds. So the results were that the pigeons quickly learned to peck at the red disc and ignore the green disc. And gradually, the green disc was brightened and its presentation extended without causing errors. So unlike pigeons trained in traditional ways, those who were trained using the errorless procedure displayed no emotional reactions, such as wing flapping or foot stamping. Another study actually looked at this in preschoolers. So researchers used errorless discrimination training to teach preschool children to distinguish between subtle color differences. So children that were trained with the errorless procedure made fewer errors and learned the task faster compared to traditional methods. And they also compared to children that were trained using traditional discrimination training, became less upset. They failed to, bang the lever, right? So they were reinforced when they pressed a lever when a particular color was present, but not when a similar color was present. And so they were less likely to bang the lever and show other signs of aggression and hostility with the errorless discrimination training, just like the pigeons. So they also looked at errorless discrimination training to teach children with incontinence to recognize the correct times to use the toilet. So the presence of cues and gradual introduction of distractions helped minimize errors during training. And this approach led to faster acquisition of toileting behaviors and reduced emotional distress. Gabois and Reeve in 2014 also used this procedure to train dogs to detect explosives by introducing incorrect scent cues in a weakened form and gradually increasing the salience of those incorrect cues. So dogs made fewer errors and learned the task more efficiently and showed less frustration during training compared to traditional methods, right? So again, why is errorless training so effective? It minimizes errors, which lowers the likelihood of making incorrect associations. It also allows for faster and more accurate learning. It reduces adverse emotional reactions like frustration, and it also has broad applicability. So it's been used across species in many different contexts, and it also has applications beyond the laboratory, right? So in education, it can teach subtle distinctions, such as between phonemes in language learning. It can also reduce maladaptive responses in individuals with developmental disabilities, and it can be used in training service animals or even safety to workers who work around hazardous substances. So, kind of a conclusion is that errorless discrimination training, as pioneered originally by Terrace, is a powerful method for teaching discriminations with minimal errors and emotional frustration. Um, and it has both scientific and real world implications. So, thus far, we've talked about a number of different ways that learning theorists can manipulate conditions so that animals learn to make some kind of discrimination more quickly, right? So, one of the ways we can do this is by varying the nature of the consequences. Um, And this is a way to improve the rate of discrimination learning, right? So what do I mean by that? Well, in one experiment, rats could press one of either of two levers. So when a light came on, pressing the lever on the left earned reinforcement, but when a tone sounded, pressing the lever on the right was reinforced. So in this experiment, there were different consequences for each of the two responses, right? So pressing the lever on the left when the light sounded resulted in earning food, and pressing the lever on the right when a tone sounded, or excuse me, I got that wrong. Right, so when a light came on, pressing the lever on the left earned reinforcement, but when a tone sounded, pressing the lever on the right did, right? But in addition to the contingency, right, they also manipulated the consequence, right? So when the light came on and the left lever was reinforced, they earned food. Whereas when the tone came on and the right lever, pressing the right lever, earned reinforcement, they were given sugar water. And so this resulted in the rats learning to very quickly make the appropriate discrimination between the lever on the left and the lever on the right. And they achieved a fairly high level of accuracy, um, or they achieved a higher level of accuracy than rats who were given the same reinforcer for each response. Right? So one of the ways to make sure that an animal learns to discriminate easily and quickly and accurately is to vary the consequences for each reinforced behavior. And that's referred to as the differential outcomes effect. So normally training is more effective if reinforcers follow behavior immediately, right? So when we can keep the contiguity fairly low, or the amount of time between the behavior and the response fairly quick, right? That results in maximal reinforcement. But when it comes to the differential outcome effect, it's actually easier for animals to learn to discriminate when you have one response get reinforced immediately and one response get reinforced after a delay. So, for example, Carlson and Richard Weikowitz in 1972 performed an experiment and found that animals receiving immediate reinforcement for one behavioral response and delayed reinforcement for another behavioral response learned to distinguish between two stimuli much faster than the animals receiving immediate reinforcement for both. So thus, the way that discrimination training occurs can have pronounced effects on learning. And this has implications for human behavior too. So for example, children with autism show improved learning when taught using differential outcomes. So it turns out that varying the consequences of different responses results in better discrimination between stimuli, not just for simple things like lever pressing, but also for fairly complicated discriminations. So for example, in one experiment, two pigeons first heard an excerpt from Bach, and then they heard an excerpt by another musician whose name I can't pronounce. So basically they had one song that was played by a flute and one song that was played on a viola. And so once they had heard both of the excerpts of music, when Bach played, pecking a disc resulted in food. But when the other song played, pecking produced no food, right? So we have differential outcomes again. We have reinforcement and no reinforcement. So by the end of the experiment, after many trials, both birds in the experiment, both of the pigeons responded with the correct response 80% of the time, okay? And were thus able to discriminate between the two pieces of music. In a second experiment, the researchers used a similar procedure, and they used two discs, and they randomly alternated excerpts between Bach and another musician. So when the birds heard the song by Bach, pecking the disc on the left resulted in food. When they heard the other song, pecking the disc on the right got food. And if the bird pecked the wrong disc, not only did they not get food, they also had to wait a number of seconds for the music to turn back on, right? So they basically got a pause in reinforcement, which animals really don't like. So they learned very quickly to discriminate between the two pieces of music. And this particular experiment, they used pigeons. They had 5 pigeons in the study, and 4 of the 5 pigeons responded correctly 70% of the time. In another experiment, researchers were able to teach fish to discriminate between classical and blues music. And in another study, Japanese researchers trained pigeons to distinguish between paintings by Picasso and paintings by Monet. So in this case, they learned to discriminate, again, based on differential outcomes. So pecking a disc resulted in a reward of grain, but only if the pigeons saw a painting by the correct artist. For 4 of the birds, this meant pecking when they saw a painting by Monet, and for the other birds, it meant pecking when they saw a painting by Picasso. So if a bird pecked when it saw the wrong kind of painting, it got nothing in terms of reinforcement. So the training continued until the birds responded correctly more than 90% of the time. And so after these experiments, the researchers ran tests using new pictures by the artist to determine the basis on which the birds were able to discriminate between them. Perhaps the birds differentiated based on color, right? So the 2 different artists might have had different color preferences, and that's what cued the pigeons when to peck, right? To test this idea, the researchers presented monochromatic paintings that were basically in black and white, but interestingly, it made little difference. The overall success rate of discrimination declined slightly, but all of the birds continued to discriminate between Picasso and Monet. So the researchers thought, well, maybe the birds were responding to differences in the contour of the lines, right? So Picasso's paintings tend to have very sharp edges, where Monet's paintings, like all Impressionist paintings, have kind of a softer, wavier look to them. So to rule out contour as the basis for discrimination, the researchers presented the images kind of out of focus or blurry. And again, they found that the birds were still able to properly distinguish between Monet and Picasso. Right? So the researchers tested other possible cues, but it does not appear that the birds responded to a single feature of either kind of painting, but rather a myriad of features. And there's been subsequent evidence to support this. So for example, you can teach rats to bar press based on whether they see different locations on a university's campus. You can also teach rats to distinguish between letters of the English alphabet and letters of either the Dutch or Japanese alphabet. So discrimination learning has been demonstrated in a wide variety of circumstances. So another example of discrimination training that kind of goes beyond the laboratory is things like learning a second language in adulthood, right? So oftentimes this can prove difficult because of differences in the sounds of 2 languages. So for example, individuals who are native Japanese speakers sometimes find it difficult to differentiate between English L sounds and English R sounds. So James McClelland and colleagues in the early 2000s used discrimination training in an attempt to teach this skill. So they used training, they attempted to train native Japanese speakers living in the United States, and training consisted of listening to a tape and indicating which of the 2 words, one starting with L and one starting with R, they heard. For some participants, the 2 words included rock and lock, and for others, the words included road and load. Some participants got immediate feedback after each attempt, others did not. The training consisted of only 3 20-minute sessions, yet the participants showed marked improvement. And those who did not get feedback showed far less progress. So this research and other work on discrimination training has important implications not only for second language learning, but also for education and learning in general. So being a car mechanic, for example, requires knowing the parts of an engine and how they relate to each other. Achieving that involves learning to discriminate among various parts. So discrimination training has also proved useful to teach both humans and animals a variety of tasks. So for example, if you want to teach a dog to be able to sniff out illegal drugs, right? They have to learn how to distinguish between various odors. And some animals with a very keen sense of smell can even locate landmines, right? So, for example, the African pouched rat, which is a large rodent, can be learned to sniff out landmines and protect people in the military, right? And that involves discrimination between explosive substances and other substances. And the training for this task begins in the lab and then goes into the field before the real work begins, right? So first, animals learn to detect the presence of TNT, for example, and indicate its presence by scratching on the ground for 5 seconds. And when this discrimination training works effectively, right, the reinforced stimulus reliably predicts a rewarding consequence, right? So when the animal successfully detects TNT, that detection behavior of scratching is going to be met with reinforcement. So another area where discrimination training is really, really effective is when you're trying to introduce an animal to a concept, right? So you're trying to teach an organism to understand a particular concept, right? So concepts essentially require the learning of two different processes. So first, in order to learn a concept, you have to be able to generalize within a category. So you have to be able to recognize that a variety of items belong to the same category, right? But you also have to be able to discriminate between items of one category and another category, right? So to understand the concept of spider, one must recognize many different types and species of spiders that might have different perceptual features, right? So a daddy long legs, for example, is a very tall spider with very long legs, whereas some tarantulas have very short legs, right? So generalization would be recognizing many different types of spiders that might not all look the same. But you also have to be able to distinguish spiders from other types of insects, for example, right? So you distinguish spiders from, for example, like an ant or an aphid, right? So how does this relate to discrimination training? Well, again, this can be used as a tool. Discrimination training can be used as a tool to help animals learn various concepts. All right. So the defining feature of concept learning allows us to discriminate between the members of one class from members of another. So for example, all spiders have 8 legs and that distinguishes them from other animals, including insects, which have fewer or more than 8 legs, right? So how would we utilize discrimination training to teach an animal about a concept? Well, the first person to demonstrate this was Kenneth Spence in the late 1930s. So he taught chimpanzees the concept of larger than. And the way that he did this is he gave the chimps a simple choice task. So they had to choose between metal covers of different sizes, and food was always hidden under a metal cover that was larger. Okay, so if the chimps chose the largest cover and pulled it off of the table, they would receive food. So very quickly, the animal was able to learn what larger is, or larger than means. And again, this is discrimination training, because if they were to choose one of the smaller covers, right, they would lift it up and there would be no food hidden underneath, right? So we have discrimination because we have different consequences depending on the particular behavioral response or the choice that they make, right? So what other things did they find? Well, Spencer found that chimpanzees learned to select the larger cover even when new size combinations were introduced, right? So even when they gave the chimpanzees a selection of all new sizes that they weren't exposed to during training, they were still able to pick the biggest one, right? So very clearly they had understood the concept or the notion of bigger than or larger than, because even when they were exposed to completely different stimuli, they knew to choose the bigger of the covers, right? Another example with Wolfgang Kohler. So Kohler, 2 years later in 1939, used chickens. And he had the chickens select between pecking 2 gray squares. And the squares differed in how dark the color was. So food was only given when the chicken picked the lighter gray square. So as a result, the chicken consistently chose the lighter square even with novel stimuli. So even when they saw different colored other shapes that were different colored, that weren't squares, and even when they were other colors besides gray, the animal still learned to generalize that concept to other shapes and other colors, right? Like picking the lighter purple of 2 purple triangles, or the lighter circle of 2 red circles. So reliably, they had learned not just to recognize a familiar stimulus, but to distinguish between both familiar and novel stimuli based on a certain dimension. Richard and Maria Mallow actually were able to do the same thing and teach the concept of sameness. So with their method, instead of using chimps or chickens, they used pigeons. And so they had pigeons peck keys with matching or differing colors. So food was provided when they pecked 2 discs in succession of the same color. So the result is that the pigeons learned to peck more often when the colors matched, even when totally new color combinations were given, than when they didn't match, right? So again, we see consistent evidence of concept learning as a result of discrimination. What about more complex examples? Well, Richard Herrnstein and colleagues managed to teach pigeons the concept of human, right? So pigeons viewed images with or without humans, and pecking when a human was present yielded a food reward, but if a human wasn't present, they didn't receive a reward. So the results were that the pigeons discriminated human images despite the fact that there was considerable variability in the stimulus, right? So they learned to detect humans um, uh, of many different dimensions, right? So humans that were a variety of races, that were of genders, that were wearing different types of clothing, right? So they were able to learn what the concept of human is, even with considerable variation within the category. And the mistakes that they made mirrored the same mistakes that would occur in other contexts. So, for example, humans make errors such as reacting to associated objects or houses rather than the human features, right? So they were able to, another way of thinking about it is they were able to learn concept learning in the same way that humans are able to learn concept learning, in the sense that they showed very similar errors. So in one experiment, researchers were able to teach pigeons the concept of tree. So pigeons pecked accurately at trees at a light when a tree was present, even with unseen images containing trees. And they were also able to identify location. So birds pecked the part of an image containing the concept, right? So if the concept was a human, they would peck at the human. If the concept was tree, they would peck at the tree without specific reinforcement for doing so. So it was very clear from this spontaneous picking of different objects in the image that they were able to make that discrimination. Right? So both pigeons and primates have demonstrated an understanding of diverse concepts including fish, cats, flowers, ships, cars, and even letters. And these studies challenge past skepticism about animals' abilities to grasp complex concepts. So the implications, right, is that concept learning can be viewed as a learned behavior, okay? So enables experimental study of concepts, and this also helps to identify practical methods to teach and improve conceptual learning. So while animals can master certain concepts, human abilities still far exceed those of animals in complexity, right? So for example, humans have the ability to generalize beyond very simple, concrete categories like trees and fruit and people and animals to very abstract categories such as justice or peace. Right? And these findings highlight the value of studying concepts experimentally, both for theoretical and applied benefits. So now that we've talked about both generalization and discrimination, it's time to talk about our last concept, which is stimulus control. Right? So stimulus control is a particular situation. So when discrimination training brings behavior under the influence of discriminative stimuli, we say that stimulus control has been achieved. So for example, rats who press a lever when a light illuminates but not when the light remains off, right? Or when a person driving stops their vehicle at a red light and accelerates only when the light turns green, or when a person enters stores with an open sign but not stores with a closed sign, we say that stimulus control has been achieved. So when our behavior, another way of thinking about it is when our behavior is determined solely by either the presence or the absence of a particular stimulus in our environment, then stimulus control has been achieved, right? So why might both humans and animals want to achieve stimulus control? Well, there are a number of different benefits to the organism. So for example, keeping us from wasting our time and energy in a behavior when doing so is futile or doesn't result in any kind of reinforcement. It allows us to travel more safely and efficiently by reducing traffic signals or preventing unwanted accidents, right? So it's very logical, right, that being able to discriminate between stimuli or being able to discriminate between environmental factors that will lead to a rewarding outcome and environmental factors that won't lead to a rewarding outcome is very advantageous. And so this is a bit of an aside. But some of you who may have taken other classes with me may have seen a magazine cover that I have in my lab space. And it's actually a cover of Time magazine with B.F. Skinner on the cover. And in it, or on the cover, it's a quote, and the quote from him says, there is no such thing as free will. Okay. And so basically the essence of Skinner's argument is because all organisms fall under stimulus control, nothing that they decide to do is freely of their volition or of their own choosing, but rather a function of a variety of different operant and Pavlovian principles that govern their behavior. So one of the concepts that your book uses to illustrate this idea of stimulus control is smoking behavior. So hopefully most of you know enough about science at this point not to be consumers of tobacco. So you know that tobacco and nicotine are carcinogens, and that they've been linked for decades to not only cancer, but a number of other really, really serious diseases. But those that do choose to smoke at some point in their life often find it very, very difficult to stop smoking. And in fact, it's so ubiquitous that Mark Twain is quoted as saying, "It's easy to quit smoking. I've done it hundreds of times." Right? So this quote kind of highlights the challenge of quitting due to the reinforcing nature of smoking. So how does this illustrate stimulus control? Well, smoking is highly, highly reinforced, right? So think about somebody that smokes a pack of cigarettes a day. That's essentially 73,000 instances of reinforcement per year, right? And so over 10 years of moderate smoking would account to 730,000 individual instances of smoking behavior followed by reinforcement, right? So heavy smokers that smoke 2.5 plus packs a day may experience 1.5 million instances of reinforcement in a single decade, right? So this is a highly reinforced behavior. And we know that reinforcement strengthens behavior, making smoking highly resistant to change, right? So one of the reasons why it's so difficult to stop smoking is, number one, that with continued reinforcement, right, that behavior becomes more and more resistant to change. But number two, there's also a very high risk of relapse, owing most predominantly to withdrawal from nicotine. So quitting essentially involves overcoming nicotine's physiological effects. So relapse weeks or months later is often mistakenly attributed to weak character, right, or not having enough discipline, which is a very unhelpful label and doesn't actually reflect what truly happens and what makes chronic users of tobacco so much more likely to experience relapse. So, for example, environmental factors like drug-associated stimuli and social pressure can seriously influence smoking behavior. So what exactly do I mean by stimulus control in smoking? Well, there are numerous environmental events that have been associated with smoking, and those gain control over behavior. So, for example, common triggers might be upon waking. If you have a cigarette first thing in the morning, if you have it with coffee, if you have it after meals or during breaks at work, or after socializing or after a stressful experience or physical exertion, right? If you smoke, if you socialize with people that smoke, right? And smokers often describe triggers as reminders that create cravings for cigarettes. Right? So, for example, seeing someone light a cigarette can act as a discriminative stimulus for smoking, even if the person has recently smoked. So, related to relapse, Brandon and colleagues in 1991 found that people who had quit smoking and smoked a single cigarette in a familiar setting, 91% of those individuals who smoked a cigarette in a familiar setting resumed resumed regular smoking, and nearly half relapsed within a day of smoking a cigarette in a familiar environment. Similarly, Bliss and colleagues found that the presence of other smokers was a common trigger for relapse, right? So what are the practical implications, right? Well, the first practical implication is to avoid potentially triggering situations. So eliminate exposure to discriminative stimuli. Other things that you can do are to avoid situations like that are common triggers. So eliminating, for example, alcohol, if that's also a trigger for smoking. But fortunately, gradual exposure to trigger situations, just like we saw with drug addiction, can be helpful, right? So drinking coffee in a therapist's office without smoking, for example, can gradually expose someone to triggering situations in the safety of a practitioner's office without resulting in relapse. Repeating training in other contexts, right? So, for example, going to a restaurant and not smoking after the meal, Or maybe we could use virtual reality training where we expose people to maybe a bar where people are smoking, and we try to use various methods of dealing with those cravings, those nicotine cravings, without having the people actually smoke cigarette, right? So repeated exposure reduces the power of the situation to elicit smoking behavior. So broader applications of stimulus control, we can look at other addictions. So for example, gambling. So specific settings and cues like casinos and slot machines influence behavior alongside the typical reinforcement schedules, right? With overeating, environmental cues like an empty plate or bowl can act as signals to stop eating. So, for example, people ate more from self-refilling soup bowls as no cue was indicated when to stop. So a strategy might be to serve smaller portions to limit calorie intake, and also to give those visual cues of the bowl being empty or the plate being empty and signaling fullness, right? So basically, in summation, people often relapse when they attempt to quit smoking because of stimulus control. Their physical environment provides cues for smoking, such as other people smoking, smoking in situations that you previously smoked, such as when you're drinking coffee, drinking alcohol, taking a break at work, doing something that stresses you out, like maybe doing your taxes or paying your bills, right? So thinking of smoking relapse as stimulus control has implications for quitting, right? So avoiding situations where you've smoked in the past or undergoing training with a psychotherapist to be able to exert power over those situations and deal with cravings without actually engaging in smoking behavior. Okay, guys, this is the end. I apologize for the information overload, but this will cover everything that you need for the exam. And you're welcome to come talk to me if you have any questions or concerns. And I hope you have a great Thanksgiving. So I asked Microsoft Copilot, to generate an AI image of a turkey, a lever pressing turkey, and this is what it came up with. And I honestly can't decide if it's innovative or disturbing. Either way, happy holidays, and I will see you next week.